All right, guess what, guys? Mrs. Lincoln's class is way ahead of us. Way ahead of us. So I guess we should try to catch up with them because we don't want them to have to slow down. No. All right, so it's time to look at the graphs real quickly. And we've kind of been doing this all along. So the blue graph there, if you look at it, it's of the form b to the x. And, of course, because it's growth, the base has to be greater than 1. You know that. What's the y-intercept of the blue graph? 1, right. So if you ever want to get the graph of an inverse function, and I think we've talked about this before, all you have to do is reflect that graph magically across the line y equals x. Y equals x becomes the mirror across which you reflect the graph to get its inverse. And the reason is the inverse of y equals x is itself. It's its own inverse, and it's also the identity graph, okay? So it doesn't change the values. And so when you reflect the blue graph across the yellow line, y equals x, you get the pink graph, right? And you can kind of see that. If you turn your hand at a 45-degree angle, you're like, yeah, I could see folding it and getting that. All right, so what happens then is all the x information becomes y information and vice versa. So the horizontal asymptote on the exponential function becomes a vertical asymptote on the log function now that has the exact same base b. The y-intercept of 0, 1, of course, we said yesterday becomes the what? The x-intercept of 1, 0. Yeah. So everything that's xy about one becomes y on the other, all right? And the base stays the same. Now what we want to do is compare growth rates for logs. We said for exponential growth, the bigger the base, the what of the graph? Do you remember that? The steeper the graph, right? So 3 to the x grew faster than 2 to the x, all right? But look what happens here with the logs. Look at the bases here. Base 2 is on the top there. You can barely read. The resolution is horrible. Base 2 is on the top, and let me highlight that. Base 3 is below that. Base 5 is below that. Base 10 is below that. Okay, logs are the inverses of exponential, right? So what can we say here? For log functions, comma, the blanker the base, comma, the steeper the graph. Smaller. Yeah. You filled that blank in before I finished writing it. That's good. We'll switch flavors here. Smaller. Cranberry flavor. All right. So that's realistic, right? If exponentials were the bigger the base, the steeper the graph, then as you reflect those across the line y equals x, they're going to be closer to the x-axis. So it's the reverse, if you will, or the inverse. So for log functions, the smaller the base, the steeper the graph, okay? The smaller the base, the steeper the graph. But notice they all share one common characteristic, or two common characteristics. When they're the form log base b of x, of course, where b is greater than 1. They're all growth, because the base is bigger than 1. They all pass through what common point? 1, 0, right? Because we've already seen that. What's log base 3 of 1? 0. What's log base 5 of 1? 0. And what else do they all have in common? Look to the left of the x-intercepts. Where are they all going? Not a horizontal, but they all have a vertical asymptote on the y-axis at x equals 0. Okay? They all have a vertical asymptote at x equals 0. All right. If you were to actually flip those around and have it log base a half, log base a half, log base a third, you would get the logarithmic decay functions, okay? So we haven't looked at those yet, but if the base is between 0 and 1, then just like exponentials, if it's between 0 and 1, it's decay, they're decreasing. Same thing for logs. If you get a base that is between 0 and 1, you get a logarithmic decay function, okay? And it looks something like that. Still has the vertical asymptote at x equals 0 and still passes to the point 1, 0. Okay, so what we want to do now, since we kind of have a general idea of what those functions look like, we want to sketch transformations of those, okay? So we want to sketch the graphs, show the asymptote, the y-intercept, and then we want to find the domain and range and look at the end behavior. Okay, letter A, number 7A. F of x equals that. Okay, sweet, awesome. Step 1, pick your flavor, okay? I'll choose teal. Okay, teal. Step 2, identify the parent function. What is it? Log base, not E, but 3. Log base 3. Is that going to be log growth or log decay? Yeah, logarithmic growth. So there's the 0.10. You could just draw it like that. That could be your parent function, log base 3 of x. And again, all log base bigger than 1 of x can have the same general shape. We don't really care about the steepness, remember, unless we're showing more than 1 on the same graph. Then we show the relative steepness. So that's what you're starting with. That's the shape that you're starting with. Okay, what would the negative 2 do in front to any function, including this one? Reflect it across the x-axis. So notice that'll make it now a logarithmic what? Decay. Good. What does the 2 do? Vertically stretches it by a factor of 2. So that's going to get steeper. That's going to get steeper. This stays the same. So it's going to look something like that. Do we typically show that? No. We don't show that qualitatively. So it's going to have the same shape. So that is our final shape. That's it for the dilations and reflections. Now all we have to do is plus 4. What does the plus 4 do to it? Moves it left 4 units. That's important because that is going to change the all-important vertical asymptote, which always starts at x equals 0. So let's go to our final graph. Here's how we would sketch our final graph. Y-axis, snap. X-axis, snap. Draw your vertical asymptote first. Okay? That's the easiest thing to do. So if it was at 0, we move left 4, where's your new vertical asymptote? Negative 4. So I'm just going to call that negative 4, and then boom. And where's the new y-intercept? If the old y-intercept was at 1, 0, and it didn't change on the dilations or reflections, and I moved it 4 to the left, where's it at now? Negative 3. Right. So if you want to label that negative 3, you can. That's not super, super duper important at this point. But it is important to know that the graph lives to the right of the vertical asymptote, and it's a decreasing function. So it looks something like that. Now notice there is a possibility, a slight possibility, that it could cross the y-axis in positive land, yes? If you grab that graph and you shift it up, it could have passed in positive land. I have it drawn passing in negative land. What should we do to make sure? We should plug in a what for x? 0. Let's try it. Let's find the y-intercept. F of 0 is negative 2 log base 3 of 4. Log base 3 of 4. What's log base 3 of 4 equal to? 3 to what power is 4? It's going to fall between which two integers? 1 and 2, right? 3 to the first is 3, too small. 3 to the 2th is 9, too big. So log base 3 of 4 is 1 point something. What's 1 point something times negative 2? Negative 2 point something, right? So what's important is not the value, but the fact that it's what? Negative. So I'm going to say it's less than 0. That's the exact answer, right? Negative 2 log base 3 of 4. You should be able to determine if it's positive or negative. So is my graph okay, passing in negative lane? Yeah, if you want, you can even label it. You can label it right there. You can label it 0, comma, negative 2 log base 3 of 4. Okay, and I guess we could label this one negative 3, 0. We're not always going to be able to follow where the x-intercept goes if there's some kind of like horizontal dilation. But in this case, we know where it's at. All right, so let's go ahead and find the domain. What's the domain of this function f? We get that from the graph right now. Greater than negative 4, right? It lives to the right of the vertical asymptote. Is it greater than or equal to? Greater than. Good. What's the range? All real numbers, all day long, right? Let's look at the end behavior, okay? So let's do the right end behavior first. What's the limit as x goes to positive infinity of this function's name is f of x? Hop on the graph, head out to the right. Where are the y values heading? Negative infinity. They're going down, down, to down, to down. And here's an interesting question. What is the limit as x goes to negative infinity? When we talk about the left end behavior of the graph, we're not talking about the leftmost point on the graph, which would be -4. We're talking about way over here at negative infinity. Does the graph even live out there at negative infinity? No. So you would say what here? D, N, E. It's in the game, right? What's that? Why would it not be -4? Okay, -4 is the leftmost point on the graph. And when we talk about the left end behavior, we're looking as x goes to negative infinity. Is -4 anywhere close to negative infinity? No, negative infinity is way over here. Okay, and the graph doesn't live over there. So the left end behavior does not exist because the graph does not live out in that direction. There is no left end behavior. So remember, D and E is a catch-all category. Limits can fail to exist for many different reasons. Let's answer this question. What would be the limit as x approaches -4 from the right-hand side? What would be the limit as x approaches -4 from the right-hand side? Hop on the graph to the right of -4 and start heading back towards -4. Where are the y values going? Up, 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 up to infinity. Now remember, when we say the limit is infinity, we're also saying the limit does not exist. But it's for a very different reason. The limit doesn't exist now because the y values are going up forever. There is no limit to how high they can go. Over here, when we say the right-hand behavior is negative infinity, D and E is also an acceptable answer because infinity is not a limit. Okay, so it doesn't exist for a very different reason. Okay, so D and E is a catch-all category. All right, anything else you want to talk about this graph? All right, let's look at something here. We've always been finding domains this year algebraically, right? Correct? Right? We don't want to divide by 0, and we don't want to take square roots, fourth roots, or even roots of negative numbers. So we've practiced that. We're experts at that, right? Logs have restricted domains too, don't they? They only live on one side of their vertical asymptote. Is there a way then to determine the domain of a log function prior to graphing it? Look at our graph and see if you can make any connections. Our vertical asymptote was at -4. How do we know it was at -4 from the equation? It was x plus 4, right? How do we know it lived to the right of the vertical asymptote and not the left? How would it live to the left? What would I have to do to this graph to make it live to the left? I would have to reflect it across the y-axis, which means there would have to be a negative in front of the x, yes? Okay, so those are the two most important things for determining the domain, right? Where's the vertical asymptote, and does it live to the left or right? Here's all you have to do. Take your argument, right? We call that the argument. It's the thing we're taking the log of. What types of numbers can we take logs of? Positive numbers. So, if you're trying to find the domain of a log function algebraically, here's what you do. All you have to do is take your argument, the thing you're taking the log of, and set up an inequality by saying it has to be strictly greater than 0. Remember, for square roots, we said greater than or equal to 0. You can take the square root of 0. Can't take the log of 0, though, right? So if we set up our argument, we say it's strictly greater than 0, let's see if that works. I got x plus 4. I say it's greater than 0. Can I solve that one algebraically? Yeah, the only types of inequalities we can solve algebraically are linear. That one's linear. So if we solve it algebraically, it's an inequality. We get x is greater than -4. Greater than -4. Is that what we got from our graph? It is, right? It is. So, boy, that's nice when the two answers jibe, right? When they're the same. Yeah. Okay, so I would encourage you then to find the domain first, then sketch your graph and compare it to what you found algebraically. You're probably going to trust your algebraic calculations maybe more than the graph. So if the graph is different from what you found algebraically, maybe your graph is incorrect, okay? Or maybe it could be algebraically, you forgot to flip the inequality if you multiply or divide by a negative. All right, so let's move to example B. What's this function's name? A, right? Of x is the independent variable. Okay, is it parent function? What's the parent function? Let's bless you. Wow. Yes, the parent function is y equals log base 0.5 of x. So let's quickly sketch what it looks like. It's of the form log base b of x, so it has a vertical asymptote on the y-axis, and it passes through the point 1, 0. But is it logarithmic growth or logarithmic decay? Logarithmic decay, so it looks like that. All right, let us find the domain of the transformed function a of x, shall we? We shall. What is the argument? 4 minus x. So over here I'm going to say I'm working on the domain. I'm going to take the domain 4 minus x and say that it's what? Strictly greater than 0. I can only take logs of positive numbers. Can I solve that one algebraically? Yes, it's linear. So negative x is then greater than negative 4. And now I solve for x by multiplying or dividing both sides by what type of one? Negative 1, which means I have to do what with the inequality? Flip it. Good. So x has to be less than positive 4. That's the domain. So d sub a, not f, d sub a is the set of all x such that x is less than 4. That would kind of imply that the graph lives on which side of its vertical asymptote? The left side. Okay. Let's see if, in fact, it does, indeed, in fact. All right, let's put it into standard transformation form, because I don't believe that it is yet. The one in the front, where does he supposed to go? In the back. He's a d value. So it's 3 times log base 0.5 of something plus 1. Now, remember, all the fun for putting things in standard transformation form typically takes place inside the function. I got 4 minus x. First thing I need to do is put the x term first. That's negative x plus 4. So I just commuted the terms. The x was negative, the 4 is positive, and it still is. Is that then standard transformation form? No. I need to, remember, make inside the coefficient of x needs to be a positive 1. It is currently a negative 1. So inside I must factor out that negative, which makes it now parentheses x what? Minus 4, close, plus 1. All right, so let's go ahead and talk about what these transformations do. What does the 3 do to our parent function log base 1 half to the x? Vertically stretches. Okay, so it just makes it look like that. We don't really care. That doesn't change the shape. It's just steeper. But what does the negative in front of the x now do? Flips it across the y-axis. So yeah, now we've got it living to the left of the vertical asymptote. Where did the X-intercepts go? If you reflect 1, 0, it's now at negative 1, 0, right? Okay. And when you do a vertical stretch, remember it doesn't change the y value, or doesn't change the x value at all, and it doesn't change the y value on the x-axis. So that didn't affect it. The horizontal dilation would, though. Okay, and so now we pick that graph up and we move it where? Right 4 and up 1. Now up 1 is going to change the x-intercept, unfortunately. Okay, when I move it up 1, you can see that it moves it. So I'm not going to track that x-intercept anymore. I can go straight to my final graph. All we're interested really is in the shape, and do we have it crossing the y-axis in the right location. So there it is. And now the vertical asymptote is at where? If it was at 0 and we moved it right 4, now it's at 4. So draw that first, because an asymptote kind of is a guideline for the graph. You want to draw it approaching it. And of course, it lives to the left, and so it's going to do something like this. And I have it again crossing in negative land. We're not going to track the x-intercept. But the y-intercept is important, because remember, I moved it up 1. And if I move this up enough, that can make the y-intercept positive. So let us check real quickly the y-intercept. How do I find a y-intercept? Plug in a 0 for x. Now, it's probably easier to do it on the original one. So let me do it up here where I have room. A of 0 is 1 plus 3 log base. I'm going to write it as 1/2. It's easier for me to think about it that way. Of 4. All right, so now this is where our understanding of logs comes in without a calculator. 1/2 to what power is 4? I could have given you that on the quiz yesterday. -2. Very good. Very good. Y'all are getting really good. That's -2. It has to be negative so that we flip the 1/2 to become a 2, and then 2 squared is 4. So that's actually equal to -2. What's -2 times 3? -6. And what's 1 minus 6? -5. So in that case, we don't have to just get the sign. We get the actual number because it was a log that we could simplify. But it is, in fact, negative. So we were in the right spot. So I'm going to go ahead and label that as 0, -5. Now, the x-intercepts are not going to be as easy to find. You're going to have to solve a log equation to do that, and we're not going to do that here. But let's go ahead and find the domain from our graph. What's the domain from our graph? Set of all x such that x is less than 4. Is that the same thing we got algebraically? Yeah. Life is good. What's the range of A? All real numbers all day long. What would be the limit as x goes to infinity of A of x, Caitlin? D/N/E. Excellent. This graph does not have right-hand behavior because it stops at +4 and doesn't live to the right of +4. So as we go out to infinity, there's nothing to go out on. So it's D/N/E for a very different reason. There is no graph there. What would be the limit as x goes to -infinity of A of x? Charles? There is no Charles in here. So anyone? -infinity. Or what's the cop-out answer on a free response? D/N/E, right? But that wouldn't be a multiple choice answer, okay? And then it's always good to talk about the vertical asymptote. What is the limit as x approaches 4 from the left-hand side? Infinity. Good. Or D/N/E. Oops. No. Okay, because we're going up forever and ever. Yeah, does this graph have any symmetry? Is it even, odd, or neither? Looking at the graph, does it have any y-axis symmetry? Heck no. Does it have origin symmetry? Turn it upside down, is it the same? I don't think so. So, no symmetry. No symmetry. That's okay. Not all dogs have tails. Yeah, I don't know how that's related, but anyway. I have a Boston Terrier that has no tail, and I have a boxer who has a dock tail, no tail. And then I rescued my dad's dog that he got rid of, so now I have a dog, a terrier mix, that has a really long tail. And it's weird now, I have a dog with a tail, and it's just weird for me to see it. Because I'm used to seeing butts go left and right when they wag, but if you got a tail, it doesn't, because you got a stabilizer behind you. So I'm getting used to a tailed dog, right? And he's getting used to not pooping in the house. Oh, okay. Anyway. Yeah. All right. Comments or questions on those? Fun or fun? Fun. Good. Fun. We'll add another one. Comments or questions? How's my day? So good so far. Yeah. I had to clean up two logs from a terrier. Yeah. But it was cold, so they came right up. You know, they didn't. Yeah, he sleeps in the office on the floor on a bed, but then where my desk is, I have a carpeted area. And, of course, when a dog has to poop, they don't want to poop on the floor, so they'll go over to the nice, soft carpeted area. And thank goodness he doesn't pee on that, but, you know, you're picking up like cold logs off the, yeah. I mean, we heat the office, but it's a little cooler than the rest of the house because it's on the exterior wall. So the turd was cold enough that I was able to pick it up, without it damaging the carpet, And so I was like, no, don't do that. And he's like, I have no idea what you're saying, right? So anyway, we're trying to teach him. He doesn't shake either yet. So we don't make any deals yet. Okay. Example 8. How much time do we have? We have plenty of time, right? Find the domain of the following functions. Find the domain. That's all we're doing. We're finding the domain. We're not graphing them or anything. Okay? I'm going to do A with you, and then you're going to do B on your own. Or I'm just going to set up A with you. Okay? We're just trying to find the domain. Is this a log function? Yes. What's the base? E. Okay? So we're not going to be dividing by 0. There's no risk of dividing by 0. There's no risk of square roots or even roots of a negative number. But we do have a log function, and inside of its argument, we have a variable. So what do I need to do in order to find the domain? What's it? The argument. Take the entire argument, x squared minus 9, and we say it's strictly greater than 0. Now, can I solve that one algebraically? How quickly forget? No, we cannot. We cannot. It's not linear. It's an x squared. So we solve it how? Not giraphically, but graphically, right? Giraphically would be like somehow with a long neck. I don't know how you do that. So solve it graphically. You've done it before with radicals. The only difference is with the radical, it was greater than or equal to. This is strictly greater than. So solve it graphically. Ready, set, go. You're doing it algebraically. That doesn't work. If you just take the 90 to the side and take the square root and say x is greater than 3 and x is greater than negative 3, that doesn't work. That's an overlapping interval. You got to find the x-intercepts. You got to know if the parabola opens up or down. And remember, the solution for a parabola is always either going to be outside the x-intercepts or betwixt the x-intercepts. Right? Remember? Does that ring a bell? It should. Yeah. Yeah. Thank you. My fish and more was good. That's me leaving Long John Silver's dining area. Long John Silver's. Yeah. When you go inside, you eat, and then there's a bell like that at the exit, and it says, if you enjoyed the experience, whatever, ring the bell. So that's how I got the idea. Yep. 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 If you enjoy your fish basket. Oh my goodness. Okay, how quickly we forget. What does the graph of x squared minus 9 look like? It's a parabola, right? We could factor that. That's the difference of squares, x minus 3, x plus 3. Is it okay to leave that greater than 0? Yes. It fails when you set each factor greater than 0. But once you have it factored, that's enough to get the x-intercepts, okay? What are the x-intercepts? What are the two roots? Negative 3, positive 3. The parabola opens up, down, or sideways? Up. Now we return to the inequality. I want to know where that graph is greater than 0. Is that above the x-axis or below? Yeah, greater than 0 is positive. I want to know where this graph is above. Is it going to be between negative 3 and 3? Or outside of negative 3 and 3? Outside of, right? Clearly, between negative 3 and 3, it's below. It's negative. So, it would be open circle, shade to the right. Open circle, shade to the left. Right? That's how you would do it on a number line graph. But we don't do it in a number line graph. We state it like this. D sub f is either negative infinity to negative 3 with a what? Parenthesis or a bracket? We're not including it, right? Because we want it to be strictly positive. So parenthesis, union, parenthesis, 3 to infinity. Or D sub f is the set of all x such that, and this is the disjoint case, right? So it's either x is less than negative 3 or x is greater than positive 3. The disjoint set. It's either here or there. It's not in both at the same time, so we don't write it as a compound inequality. We write it as two separate intervals or two separate inequalities. We return to the inequality, right? We always want the argument to be greater than 0. So we're always going to be looking where our graph is above the x-axis. Oh, that's a greater than. Yeah. How do I know it's outside of? We always want the graph to be positive. So where is this graph positive? It's positive to the right of 3, right? It's above the x-axis, and it's positive to the left of negative 3. Okay? We've done that. We did that a lot earlier, so it shouldn't be like, wow, I learned something today. It's like, oh, wow, I get to reuse my old knowledge. That's good. Right? The only difference is, again, they're open circles because we don't want it to equal 0. With square roots, we can take the square root of 0. We can't take the log of 0, right? So they're open parentheses or strict inequalities. All right. Letter A2. Y'all need to practice that one again. How about f of x equals 207 minus log of 9 minus x squared. Yeah, there we go. Find the domain of that one. Oh, minus, we'll put minus 3 log of 9 minus x squared. Doesn't make a difference for the domain. Find the domain, find the domain. Not x squared. Because you're factoring the x squared into x. Yeah. What'd you get? What'd you get? Is it between the x-intercepts or outside of? Between. Good. Okay, so you would show 9 minus x squared is greater than 0. Now that is also a factorable difference to squares. So you could factor it one of two ways. You could either say 3 minus x, 3 plus x is greater than 0. Or some of y'all put the negative in front and you have negative then x squared minus 9. And then that gives you negative x minus 3, x plus 3. Either way, whatever you're comfortable with. You just need that to get the roots. That's really all you're factoring for. So the roots are 3 and negative 3. And because it's a negative leading coefficient on the x squared, our parabola opens downward. Okay? And now we return to the inequality. For logs, we always want to know where the graph is above the x-axis, strictly above. And you can clearly see now that it's above the x-axis between the x-intercepts. So if you were to shade it on a number line graph, it would be open circle, and you would shade between. Okay, so this is the connected interval. This is the and interval. So if you're writing it in interval notation, it would be negative 3 to 3, like that. If you're writing it in set notation, it would be the compound inequality. -3 and 3, and x is physically between them, and then you get strict less thans in between there. So that is your compound inequality. That's the only time you use it. You should only be using a compound inequality when you have less than symbols in there, not greater than. Because if they're greater than symbols, it should be a disjoint, two separate ones. So that's the AND case. It's both greater than -3 and less than 3 at the same time. Okay, let's do one more bonus one. Okay, let's call this B of x for bonus of x, and let's let it equal 5 log base 221, log base 21 of x squared minus 8x plus 15 minus pi. There we go. This might be the last one we get to. Find the domain, find the domain, find the domain. Y'all sing when y'all do those worksheets? No? Okay. Joe, you sing a lot though, George. You just don't sing, it doesn't inspire singing? No. Oh, yeah. There's a song by Jimmy Buffett. It's called Math Sucks. Maybe you can sing that one. Math Sucks. But you know what? If you listen to it, you can totally tell that it's tongue-in-cheek. He's trying to be facetious. Right. It's actually an ode to math. Yeah. Just looking at it, you should know whether the solution is going to be between the x-intercepts or outside of. Because for a log function, we always want it to be positive. And that parabola opens what? Up or down? Up. So is it going to be between or outside of the x-intercepts? It'll be outside of. So really all you got to do is find the x-intercepts of that parabola, and I didn't make it so that it factors. What'd you get for your x-intercepts? Not -3, -5. Yeah. Because you got to move your y-axis to the other side. You don't have to put domain. If it's working on the domain, all I really want to see, like we did in the past, is your inequality. If you want to set it equal to 0 so you can factor it, that's great. But you can factor it with the inequality intact. You just can't split up the factors and say that they're each greater than 0. So that's going to be -3, -5, I believe. And so that's really all you need. You don't need to go any further than that, because that's enough to draw your graph. The x-intercepts are not at -3, -5, but at +3, +5. And you really don't even need to sketch the graph from there, but it's nice to get a confirmation on the visual. We want to know where it's positive, so it's outside of. So the domain of the bonus function is either -infinity to 3 with a what? Parenthesis, good, union, parenthesis 5 to infinity, or the set of all x such that, is this a compound inequality or the disjoint? Disjoint. So x is strictly less than 3 or strictly greater than 5. And it is impossible for a number to be both less than 3 and greater than 5 at the same time, which is why it's an or case, one or the other. Okay, so we had two separate bonus ones there. So we didn't get to this one, B, but we'll pick up with 8B tomorrow, and we should be able to easily finish the notes tomorrow, okay? So tomorrow is Friday. You should walk in ready for a quiz, right? On sketching a graph, or at least finding domains, at least of a quadratic. And if we don't have one, you're like, oh, diggity darn it, right? Kind of like what Matt Rule says when a Baylor football play doesn't go his way, right? Diggity darn it, shoot, fiddlesticks. Right? He gets angry. All right. Like, who's that guy from The Simpsons, the neighbor? Ned Flanders. Yeah, yeah.